They will rue this day. Crap. Why me?
I'm Brady Heron, and this is Professor Squidley Williamshire of Cambridge, right?
Yes,
And
this is my name.
do you think you could explain to us the physics of strings?
So, the maths behind music has always been a very interesting topic to me. Here, I think we'll just start with strings. Basically, what's happening when you pluck a string, the wave is going down the string, and then it reflects back upon itself. And when you're playing what is considered the fundamental frequency of a string, the wavelength is twice the length of the string. So now, to get straight into the maths, we're going to discuss how to find this fundamental frequency. The speed of a wave is frequency times wavelength. Alright, so solving over here for frequency, we know that the frequency equals the speed over the wavelength. Now, the speed of the wave can be expressed as the square root of the tension over the linear density.
Where does that come from?
That comes from calculus and differential equations, which we're not going to get into because this is a family-friendly channel.
Okay, but what is linear density? What is that thing at the bottom?
Linear density is the amount of mass per length, per unit of length.
Well, how can we find that? Say if I had perhaps, like a nylon string, like how would I find the linear density of a nylon string?
The linear density is the mass of the string over the length of the string.
Alright.
And the mass of the string can also be expressed as the volumetric density times the volume. So we have the linear density right here equals the volumetric density times the volume divided by the length. Now what's the volume? The volume of a string is actually pi times the radius of the string squared times the length of the string. The mass now becomes the density times pi times r squared times L divided by L. Now you can see these L's are definitely going to cancel. Now if we plug this back in to the original equation, we have the square root of T over mass over length equals square root of T over rho pi, and then we're just going to bring this R out here. This is something we haven't dealt with yet. It's the wavelength. The wavelength, as I said before, is 2L, so frequency is going to equal the speed over 2L. So now solving for our final equation, we have the frequency at the fundamental frequency is going to be equal to square root of tension over density times pi times 1 over r times 1 over 2L. So now we're going to talk about harmonics. Basically what harmonics are is, instead of just playing the fundamental frequency where the wavelength is 1 over 2L, now we can make a wave that takes up only, for instance, it could be 2 waves across the string or 3 waves across the string. Alright, so at the fundamental frequency, we have the wave starts here, right? It'll go up and down, and then it goes up and down between what this is called is the antinode. The antinode is the place where the wave is at its peak, and basically it's just going to oscillate between these two antinodes, and at the two ends of the string, which are called nodes, the string doesn't move at all because the wave is reflecting back across itself, and it causes it not to move at the nodes. So basically what can happen is, instead of just having one antinode, we could decide maybe we want to have 2. And so for the second harmonic, instead of the first harmonic, we're now going to have 2 antinodes, which means that it'll create a full wavelength across the entire string. Now, this is the fundamental, also called the first harmonic. And then this is called the second harmonic. And you can see that now the wavelength of this, instead of being 2L, is just L. because it starts here and then it ends right here at the distance L. Now at the third harmonic, we now have 3 antinodes, right? So now we have a wave that starts like this, goes down here, goes up here, and then you can see it stops, and it's just about 1.5 L is the distance of the wavelength and all that, which is because the n over 2L, which represents the wavelength of the wave, is when n equals 3, it's 3 over 2L.
Alright, so you're saying that the harmonic will determine the wavelength of the string given the harmonic number and the length of the string, right?
Right.
And how would you express that generally?
Generally, it's like I expressed it in the equation over rho pi times 1 over r times n over 2L. So when n equals 1, our wavelength is just 2L. When n equals 2, our wavelength is L. When n equals 3, our wavelength is 2/3 L. Right, because
that makes sense. Right. Okay.
the number of antinodes is increasing, and basically on a guitar string, you can force the harmonics into any certain harmonic you want it to be just by placing a string or your finger on the string at the desired position. Alright, if I plug the string without holding it down, you get the fundamental frequency because I'm not restricting it from vibrating at any particular point. However, if I line my finger exactly halfway between the ends of the string, you get the first harmonic, the second harmonic, which is an octave up from the fundamental. On the second harmonic, you can see there's a node halfway through L. So if you placed your finger right here, you could force the guitar string to be playing the second harmonic because your string would stop it from vibrating, or your finger would stop the string from vibrating right there, and it would cause the antinodes to appear right here. Alright, basically, to summarize what we've gone over so far, we have your frequency equation. T represents tension. Rho represents your volumetric density of whatever material you're using, so it's just mass per volume. Then R, you have the radius of whatever string you're using. L is the length of your string. And then N right here, N is your harmonic number. And the harmonic number basically just references however many antinodes or however many humps you have in your string. So the basic way that a string wants to vibrate, the easiest way for it to vibrate is in the first harmonic or the fundamental frequency where n equals 1, and you just have one antinode and it's just going back and forth, up and down, right? Second harmonic, which you can force it into by putting your finger in the middle of the string, causes it to have 2 antinodes and a node in the center where it's not moving. Third harmonic, similar process. It's not this one, that's wrong. It's this one where you have 3 antinodes and then you have a node, a third and a 2/3 along the way, and it just continues to go up like this, dividing the string into smaller and smaller pieces, which by the way is where the harmonic series comes from. It's 1/2 plus 1/3 plus 1/4 plus 1/5, because
it's a summation of 1 over n, right?
It's a summation of 1 over n, correct. Now basically, going on from this, so you have your frequency, you know what your frequency is from any specific harmonic you have or any specific amount of antinodes you have in your string, but what does this mean when we hear it, you know? Right, so basically, to address this, fundamental frequency, it could just be any frequency. Let's say, for example, fundamental frequency is 100 Hertz, just making up a number. Now, this is going to correspond to some note on the Western music scale. Let's say it's E. It's not E, but if I'm going to my second harmonic, right, that means n equals 2, right? So, if I multiply this F, let's just call this is just a constant because it doesn't change, right? And the 2L, in fact, doesn't change either. So, F equals K times 1, right? That was just our first harmonic when n equals 1. However, if I increase the harmonic number to 2, right, it's now K times 2. So I'm doubling my frequency, right? Now, the way our ears hear this is an octave increase in the pitch, right? So this 100 Hertz E, when I multiply it by 2, becomes a 200 Hertz, and it's still an E.
It's still 100.
Because we hear it, oh crap. Polywalker. Alright, So we double the frequency, right? But our brains still hear it as the same note, right? Because it's an octave. So now let's move on to the third harmonic, right? So now F would be whatever our constant is times 3. So it'd be 300 hertz. Now this time our brains is not going to hear it as an octave because it's not a multiple of 2 times the original frequency, right? From this E to this E is an octave, right? But what's the ratio of this E to this frequency? It's 3/2, right? Because we went from 200 to 300. Our brains hear a frequency ratio of 2 to 1 as an octave. However, our brains hear a ratio of 3 to 2 as a perfect fifth, which is just 5 notes up from whatever note you had. So seven semitones, but 5 letter named notes. All right, and then if you continue on with our harmonic numbers, right? We started with 100 hertz. We went to 200.
That's an octave, right? 200.
200, that was the octave, right? That gave us our high E. 300 hertz. Since we hear that as a ratio of 3 to 2 from that high E we just made, we hear this as a B because it's a fifth above a high E, and then it's a octave plus a fifth above our low E, right? Now, if we move on to the fourth harmonic, we're multiplying our original frequency by 4, right? That means we have 400 hertz right here, which our brains hear as a ratio of 4 to 3 from that B we just had. And our brains hear a ratio of 4 to 3 as a perfect fourth. And a perfect fourth up from B is, you guessed it, another A. Now, if we continue on, what about 500 hertz? Well, this is a ratio of 5 to 4 from this high E because it goes from 400 hertz to 500 hertz, right? Our brains just happen to hear a ratio of 5 to 4 as a major third. A major third up from E is a G sharp. Right, so we went from this E and then we went up a major third to G sharp. If you continue on like this, 6 to 5 is a minor third. Minor third up from G sharp is B, right? So that was our 600 hertz. So now we have all these harmonics, right? We have all these pitches that can be heard discreetly if you lay your finger at a specific spot on the guitar string, right? But it turns out that it's not just one of these harmonics you're hearing when you play the fundamental frequency. You're actually hearing all of them all at once, and each instrument has a specific, what we call overtone series of harmonics that are produced by that particular instrument that causes that instrument to have its timbre or the quality of its sound. So a guitar string, when you pluck it, most of the string is vibrating like this, but the wave is also, part of it is vibrating like this, part of it is vibrating like this. And all of these vibrations combine to produce the sound you hear in your ear, and it also sort of combines to make a wave that looks more like this instead of just a perfect up and down. But however, when you play the fundamental, most of the string is just vibrating with an anti-note at the top, right? Which is why the fundamental frequency is the one that's heard most loudly, and that's considered the pitch of the string.
Okay, then how would you distinguish, say perhaps, a semitone, you know, like perhaps A to A sharp, or B to C? How would you distinguish that?
Well, what Western music relies on now is something that's been developed over time, which is 12-tone temperament. Now basically, we talked about all these ratios, right? Which is dividing up an octave into smaller and smaller parts, right? However, what Western music does is it divides up an octave into 12 equally spaced tones, or equally spaced for our ears to hear. So the distance from a B to a C sounds exactly the same to our ears under 12-tone temperament as from C to C sharp. It sounds like a half step or a semitone, right? So, going off these ratios, we know we want to divide it into 12 equal tones, right? And furthermore we can divide each tone into 100 cents, right? So that means we want to have 1200 equal steps between octaves, right?
It's not in a linear fashion that you take steps along the musical scale. It's from B to C is not necessarily linear as you would going from C to C sharp because it's higher frequency.
The frequency might be different because say I had an E at 100 hertz, right? And an E at 200 hertz. This is an octave as we established because I multiplied the frequency by 2, right? But our next E is at 400 hertz, right? So the distance in hertz in frequency between these two E's is less than the distance in frequency between these two E's.
Linearly, right?
Linearly, correct.
But in ratio, they're the same distance.
In ratio, they're the same distance. So the goal of the 12-tone temperament scale is to sort of make a logarithmic type of differentiation between tones, right? Now, the way they do this is by having an equation, right? All right, so what Western music has developed is a system called sense, right? And it divides the musical scale of an octave into 12 equal semitones, right?
Yes,
right. 12 equal semitones, and each of these semitones is divided into 100 equal cents, right? So there's 100 cents or one semitone from A to A sharp or from C to C sharp, right? So, in order to do this, they've developed this equation. The number of cents separation between frequencies F2 and F1 is equal to 1200 times the log in base 2 of F2 over F1, right?
Where does the 1200 come from?
1200 because we want to have 1200 cents in one octave, right?
All right.
So 12 semitones and 100 cents per semitone, right?
Okay.
That's where the 1200 comes from. And then the log 2 because each octave is multiplied by 2 on the frequency. Now let's say we wanted a perfect fifth, right? So let's just find the sense separation equals 1200 times the log in base 2 of a perfect fifth was 3 over 2. That's the ratio, and the ratio is all that matters, right? Now, if we pull out a handy-dandy calculator, we can find that this sense separation equals 701.955. 709 between a perfect fifth. So let's say between E and B would be 701.955 cents.
Okay, so you defined a perfect fifth as 7 semitones up, right? So,
right.
Would you say this here shows that it's not exactly 7? It's 700. It's actually slightly above 700 cents.
Right. So
what does that mean?
So we have 3 over 2. That's an actual perfect fifth. That's what our brains hear a perfect fifth as. So if I had musicians that were playing frequencies at a ratio of 3 to 2, right? According to our sense system, it's actually slightly above a perfect fifth, even though that's the actual perfect fifth. However, let's say how we design our instruments is in accordance to the sense system. So a perfect fifth that a musician plays will really be a perfect fifth according to the sense system, which is 700 cents, right? Now, this 700 cents...
We should probably get your paper.
Oh, yeah. So this 700 cents a musician is playing is less than the 701.955 cents that an actual perfect fifth is, which means that a perfect fifth on an equal tempered instrument is going to be slightly flat, or the pitch is going to be lower.
So would that mean that if you were to perhaps derive a new note based on the sense system, would that be sharper or higher or lower than deriving it based on these ratios that you know of?
It's going to be actually lower.
Lower, okay.
Lower,
okay.
Because according to the ratios, if I play a frequency, let's say if I play, one musician's playing 300 hertz, one musician's playing 200 hertz, our brains are going to hear that as an actual perfect fifth. That's what sounds the best to us, because according to our brains, simple ratios sound the best, right? This is going to be 701.955 cents. But if I got a musician that was playing, or two musicians playing notes that were 700 cents apart on equal tempered instruments, the difference between them is going to be less than the actual perfect fifth. So our brains will hear it as slightly flat. As I said, the sense system is a fairly accurate system for determining the pitch.
What are you guys doing here? I need you guys to leave.
All right. Oh, these bloody American They think they can kick me out? They think they can kick me out? Professor Squidling Dumpling Shire! No!
Professor, what are you doing?
I'm gonna show these wankers how to show some respect to their elders. They will rue this day. Crap. Why me?